As we continue into chapter 4, we're going to be looking at chirality in molecules, but where there are two or more chiral centers. So instead of just a molecule with one single chiral center, we'll now be exploring multiple chiral centers. Chiral molecules that have chiral centers, we can predict how many stereoisomers there are of that molecule. So how many different isomers of different rearrangements in space, so different R or S configurations, using this simple equation, which is 2 raised to the n, where n is the number of stereocenters in a chiral molecule. So for example, a chiral molecule with 2 stereocenters has 4 possible stereoisomers. That's 2 to the 2, which equals 4. And here are those different combinations. In this particular molecule example, we have dihydroxybutanoic acid. Here there is a chiral center at position 3 and at position 2. Each of these chiral centers could be in the R or the S configuration. And so we can have a version of the molecule, a stereoisomer, that is RR. We could also have SS. We could have the 2 position be an R and the 3 position be an S. And we could also have the 2 position be an S and the 3 position be an R. So these are all 4 of the different stereoisomers that can exist when you have these 2 chiral centers. Now, we talked about enantiomers in the last chapter. And if you look at this molecule and the versions that I just showed you, where you have version 1, 2, 3, and 4, RR, SS, RS, and SR, you'll notice that the version where we have an RR and an SS are enantiomers to each other. That's 1 and 2. And also, the version where we have an RS and an SR are also enantiomers of each other. That's 3 and 4. You can see this when they're drawn out. Here, this is a hashed or dotted OH on both of these, and here they are wedged and coming forward. So either both back or both forward. Those are mirror images. And here we have 1 forward, 1 back, and 1 back, 1 forward. So these are also mirror images. But how do the other compounds relate to each other? For example, how do 1 and 3 relate? And how do 2 and 4 relate? The word for this is a diastereomer. So they are stereoisomers, but they are not mirror images. So again, these are types of stereoisomers that are not mirror images. This is just the word we use for any compound relating to itself where it has a stereoisomer that is not this mirror image version. So again, an enantiomer is a non-superimposable mirror image, and a diastereomer is a non-mirror image version. This occurs when you have multiple chirality centers. So again, here we can see that 1 and 2 are related to each other as enantiomers, and 3 and 4 are enantiomers. And 1 and 3 are diastereomers to each other, non-mirror images, and 2 and 4 are diastereomers to each other. So if we were to draw them all out and we wanted to show how they relate to each other, Here is version 1, 2, 3, and 4, and you can see 1 and 2 are enantiomers to each other, and 3 and 4 are enantiomers to each other. Remember, enantiomers always come in pairs. So that means 1 is related to all other versions as a diastereomer. It is a diastereomer with compound 3 and also with compound 4. And that's true all around. So compound version 2 is a diastereomer to 4 and to 3. Diastereomers do have different physical properties. So we talked a little bit at the end of our last lecture how enantiomers have the same properties. But diastereomers have different physical properties. This is going to be important when we're talking about how we separate enantiomers. I noted that enantiomers are hard to separate because they have the same physical properties. We can't separate them by melting point or boiling point. However, diastereomers can be separated via these. So we talked about cis trans isomerization in the past, in particular in relation to rings, where you have these fixed ring systems. So for both cyclic compounds and alkenes, which we'll be talking about in the future, we did note that alkenes are molecules that have double bonds. Cis and trans isomers are related as diastereomers. So we talked about how diastereomers were geometric stereoisomers, and this is the particular name you could use for them. They are diastereomers. They are not mirror images. However, they have the same connectivity but differ in their spatial positions. Cis and trans isomers do have different physical properties because they are diastereomers. For example, their heat of combustion, boiling point, and melting point are different. Okay, let's do some practice problems now that we've talked about enantiomers and diastereomers. Here is a Fisher projection of glucose. This is drawn out in its linear form instead of its ring form. And we want to calculate how many compounds are diastereomers of this glucose. So I've already given you one version, one molecule of glucose. How many molecules are diastereomers of this isomer? So first, let's calculate how many total stereoisomers there will be for glucose. We're going to use that equation, 2 to the n, where n is the number of chiral centers. So how many chiral centers does this molecule have? Well, if you go through, remember we want to look where it has any area where there are 4 different things attached to it. So this is a chiral center, this is a chiral center, this is a chiral center, and this is a chiral center. So there's 4 chiral centers. So this will be 2 to the 4, which equals 16. Now this is total stereoisomers. One of the stereoisomers is this molecule itself. We've already shown you one of them. This question asks how many diastereomers of this compound are there? Well, we know that there will be at least one enantiomer of this compound, one mirror image version. And that the rest of the compounds will be related to this stereoisomer as diastereomers. So in total, there are actually 14 diastereomers left over. So 16 molecules total. One of them is shown. One of them is the enantiomer of the shown molecule, and the rest are going to be diastereomers of the shown molecule. So 14 would be the answer.